In this short video, I will be disproving Cantor's diagonal argument. First, a quick refresher on the argument and what it really entails. It being a proof by contradiction starts by assuming that there is a bijection between the natural and real numbers, though for simplicity will the latter set only be comprised of the elements which are between 0 and 1. The argument now states, for any possible order of real numbers, there exists a way of generating a new real number, which is not in the list due to being different to every other element. For example, by taking a digit of every number and adding 1 to it, subtracting if the digit is a 9. Now, what often gets ignored is that this is not the only way of generating such an element. One could, for example, change the addition, the order, the way of getting differing digits, and even the amount of digits being changed per step. Fundamentally, the argument states that a set for which there exists an algorithm that generates or shows an element which is in this set, but different to every element in a countable depiction of that set, does not have a bijection to the set of natural numbers, and is therefore uncountable. Having defined the argument, how would one go about disproving it? One way would be to directly point out the fault in that logic. Another way would be to present an order of an uncountable set that does not allow for the creation of an excluded element. And the third one being to show that the exclusion of an element is also possible for a set that is thought to be countable, with this being the one that we'll be focusing on, though showing this will imply the other two, therefore we'll also take a look at them later. How do we make a set uncountable? Since a set is uncountable if there exists an algorithm phi which creates an excluded element, one could go about finding a phi for a given set. But instead of this, we will guarantee the existence of such an algorithm by defining a set around it using a recursive definition. For this, the base case will be that there exists a subset of S with at least one element. The recursive step now is that if something is a subset of S, then its union with phi over itself is also a subset of S. Two important things about this recursive definition are that first, the original subset can be finite, with it having possibly only one element, as well as phi always producing only one element and therefore also making a set consisting of only its output finite. And second, that the union is countable. Keeping that in mind, we see that since a countable union of finite sets is countable, S is countable. But since we also made sure that any number that is generated by phi and is therefore different to every number in S should be in S, this set is also uncountable. And this is not only a theoretical set, we can actually create such a set and see what elements it is made up of. For this we first need to define a base case element x. For this example we'll just choose pi. Then we'll need to define an algorithm. In this case we will first sort the elements by size, then generate the excluded element with diagonalization. There are of course other ways to achieve the same with different algorithms if one has a problem with the sorting of infinite sets. Now with the base case defined as well as the algorithm, we can, using recursive definition, finally see what elements are in such a set G. Following the steps, we find that any set of form x plus 0.1, x plus 0.11 and so on is both countable and uncountable. This is also reaffirmed by noticing that this set has a bijection to the rational numbers, showing countability. And for uncountability, we again know that there exists an algorithm that generates a number different to every other number in G, but due to the recursive definition of G, this element also has to be in G. A set being both countable and uncountable obviously renders the distinction useless, because a set can hardly have and not have a bijection to the natural numbers at the same time. So what exactly is the logical fallacy in Cantor's diagonal argument? Simply said, it boils down to a poor understanding or at least differentiation of actual and potential infinity. He states things that adopt actual infinity, meaning infinity as a number, but when it comes to the natural numbers, they are viewed as product of potential infinity, even though it is assumed that they are completely listed as well. This arbitrary distinction ignores that besides implying that there exists an element differing to the excluded element by 0, it also implies that 100% of the natural numbers are p-adic. But why does specifically this recursive definition break Cantor's diagonal argument? It works by showing the absurdity that generating a new element makes a set uncountable while excluding the most widespread form of it, counting, by making diagonalization the recursive definition of a set similarly to how counting is for the natural numbers. Finally, for how a well-ordering of the real numbers would look without the use of the axiom of choice. Knowing that the diagonal argument is false, we can simply take a normal real number like the Chabanov constant and span it over 2 dimensions. If there are any questions, do feel free to post them in the comments, as well as anything that goes in the direction of pointing out supposed faults in my logic. And if there are a lot of those, or really important ones, I'll go ahead and address them in a new video. Or in the case of this video being wrong, edit it and change the title to reflect this not being a successful attempt of disproving Cantor's diagonal argument. Though I highly doubt that this is going to be the case. Other than that, the next video probably will be about how algorithms are different to mathematical functions and the real incompleteness theorem, in which I will steerman the halting problem by exploring a fault in the original proof by Alan Turing, as well as replace Gödel's faulty incompleteness theorem, possibly showing that P equals NP cannot be disproven. See you then.